So, dear friends, today we will discuss on IR spectroscopy and how it responsible for the find out the structure of molecule. Basically, by using the IR spectroscopy, we learn in organic chemistry. It is very useful tool for find out the functional groups. If suppose carbonyl group is there, it absorb at a frequency that is 1700 centimeter inverse to the 1700 1800 up to 1800 carbonyl frequency. Ketone is absorbed at 1700 15 to the 25 centimeter inverse. If aromatic compound is there, it will absorb at 1600 centimeter inverse. Okay, by looking these values we can predict the structure, the functional groups. Therefore but IR region is a functional group, fingerprint region. Okay, the spectra definitely match with the if you take the salicylic acid spectra, then it definitely match. First spectra definitely match second spectra. That is fingerprint region. The first spectra will match the same compound. Spectra of same compound will be matched. Therefore, IR spectroscopy is very useful to find out the functional group or of a compound. Okay, some basics we will learn in this lecture. Okay, as we discussed the previous lecture, microwave spectroscopy, the range is 10 raised to 5 to the 10 raised to 7. Okay, therefore electromagnetic radiation, your microwave region is found 10 raised to 5 to 10 raised to 7. Okay, the electromagnetic radiation, that range is nothing but your microwave, and the region before microwave region, that is IR region. And for IR region, your frequency is 10 raised to 3 nanometer to the 10 raised to 5 nanometer. Such kind of frequency is wavelength is required for when you pass this electromagnetic wavelength to matter. It absorbs energy, it will goes to the next energy level, and by absorbing energy, and that is the frequency is absorption spectra, you will obtain that particular frequency, number of frequencies in your spectra. Okay, during this excitation, the dipole moment is changed, and therefore as like IR spectroscopy, only the molecule which is having the dipole moment is IR active. If suppose you have this homo diatomic molecule is there, for example H2 is a diatomic molecule and hydrogen is the same atoms, then that is the homo diatomic molecule. It is not dipole it is not having the dipole, therefore it is IR inactive. As like microwave spectroscopy, the molecule which possess the dipole moments, okay, we are thinking about the diatomic molecules. Diatomic means the di is a 2 and 2 atom is there is a 2 atom. HCl is a diatomic molecule, hydrogen and chlorine. It is having the dipole moment. Therefore, HCl is having the dipole moment. It is considered as IR active. Therefore, the dipole moment, the substance which not have the dipole moment is not IR active, and the substance which is have dipole moment is considered as a IR active. Let us start its principle, what actually happened Okay, that principle we will learn according with the physical chemistry. If suppose, okay, at this coordinate is if internuclear distance, okay, that coordinate increase the internuclear distance. Okay, the distance between, okay, if suppose that we are seen in microspectral first atom, the atom we consider the atomic molecule, first atom is joined with the second atom, and the distance between these two we consider as a internuclear distance, that is the R1. Okay, therefore internuclear nuclear distance is increases in IR spectroscopy due to absorption of energy. Its dipole moment is changed and there is a vibration takes place, and due to that vibrations your molecule internuclear distance is increases. If suppose that first molecule of the first atom is present at that position and second is present at that position, and this is our equilibrium distance. Okay, equilibrium internuclear distance, this is called as the equilibrium internuclear distance, and energy is increased from the, okay, by absorbing the energy. Okay, at that point that level, energy level is we denoted by the V, and it is equal to 0. Okay, but after absorption energy two possibilities there. Okay, that first is the we consider this molecule is joined with a spring. Okay, first assumption we consider this molecule is joined with the spring, and it's due to vibration. One end we consider as a rigid end. Okay, first end we not move the first end. We consider first end remains at the its position. Only second atom will be vibrate or change its position. Okay, first is a stationary position, it's not changed, but second atom will, due to vibration energy, due to taking energy, its length is decreases or length is the increases. Okay, therefore if it takes the energy, two possibilities there, it due to compression, okay, it may compress. Okay, if suppose it compress, okay, therefore it compress, or it okay, that same molecule, okay, that we have shown like that. Two possibilities. First possibility, it may compress or it may elongate. Okay, it may stretch or compress. Okay, we consider that molecule, two atoms is joined together by the spring. First end is the rigid, only second atom is the vibrating, or that due to that its internuclear distance will be increases or the decreases. Due to that some energy stored in the molecule, that level has the higher energy. Okay, therefore when molecule is compressed or molecule is stretched, a force is acting opposite to that particular direction. Okay, if the compressed, force is acting that direction. If it is stretched, force is acting the opposite direction, and that force is directly proportional to the your displacement. Okay, that force is restoring force, we call it as a restoring. That force try to your molecule K should be at equilibrium. That position we call it as the equilibrium position. Correct. This restoring force try to molecule came at its equilibrium position. Okay, it tries to original position. It try to molecule will be at equilibrium position. This restoring force. Okay, that is restoring force. Okay, according to the Hooke's law, we will discuss the restoring force is directly proportional to the displacement. Correct. due to compression or same energy is at that position, if elongate or it's compressed, that level has the same energy. That level is we consider as the V is equal to 1. Okay, that level is the first level. Okay, therefore we can if show like the dotted lines, okay, like that. Okay, this is simple. This is the simple harmonic motion. That molecule possesses the important thing, simple harmonic motion. Okay, simple harmonic motion means the same compress, that direction will be from the equilibrium will be same. Okay, that simple harmonic motion is there. Okay, as like in your watch, there is watch is that pendulum will be go same distance from that side, same distance to this side. That is simple harmonic motion is there for this compression and the stretching. Okay, as like your energy is increased, you increase stretching is increases, your stretching is increased, second next level you obtain, then again compression increases in this side, your at that point same energy is there. Okay, like that again it increases, this compression is there, again is elongated, and if it more and more elongated, molecule will be break. Okay, like that we have first energy level, second energy level, third energy level is there, and fourth energy, so on energy level is there. Remember that in between the vibrational level there is a levels, that is the rotational. Okay, we will discuss later, but in between molecular energy levels there will be the vibrational energy levels, and it again there will be rotational energy level. Okay, this rotational energy level is we have already discussed that things. Okay, therefore if this molecule is excited to this level, this molecule can be excited to this level. Okay, the compression is there. Okay, this is joined by the, we consider this joined by the spring is there. Okay, first thing is this is show the simple harmonic motion. Your atom is joined by the springs. First change is rigid, second one is the movable. That equilibrium position is molecule try to achieve that equilibrium position. Okay, therefore if molecule is compressed, therefore for restoring force, that is force is try to molecule put at the equilibrium position. Okay, that's molecule, if the compress try to molecule put at equilibrium position. Okay, due to that there is a frequency is there. Okay, during this excitation or first energy level, your dipole moment is changed, and your electronic components of that molecule will combine with the your electromagnetic radiation and gives the absorb that particular frequency, and it will occur in the spectra. This is important thing. Dipole moment is not for a molecule diatomic moment, it's not IR active. You should require the first important thing. Okay, now that particular frequency, okay, mu, instead of frequency the notation V or mu, we will use the notation omega. Okay, which will is required for, we will see the next IR spectra with the microwave spectra. Therefore combination of these spectra, you should require the discrimination between the frequency IR frequency and the microwave frequency. That's why we use the omega bar. Okay, omega bar nothing but the your mu bar, that is the wave number. Okay, we first lecture we said that if your molecule from one energy level to the other energy level is excited, okay, during this excitation some energy is absorbed, correct, some energy is absorbed, and that energy given by change in h mu, correct, and if delta E, that h is transferred to that side, is equal to mu, and that mu will be converted into mu bar. Therefore delta E upon h is equal to divided by mu upon c is nothing but the mu bar. Remember that delta E upon hc or the frequency upon the velocity of light is nothing but the mu bar, and that is nothing but the 1 upon lambda. This is important relation. Delta E upon Hc is equal to frequency upon c is equal to mu bar. Like that, that frequency mu we have replaced by the omega upon c. Okay, this term is called omega upon c is nothing but this frequency is centimeter inverse, and omega upon c is also in form of the centimeter inverse, but only omega, okay, omega is in hertz or cycle per second. Omega bar is equal to, okay, we replace this frequency notation, V equation, mu notation we required, but instead of we use the omega, because later we have to require for the discrimination of that higher frequency with the microwave frequency. Okay, this frequency omega, okay, omega is given by 1 upon 2 pi upon, that is your constant k, and upon mu. Okay, this is the constant, this k is also constant, mu is the reduced mass. Mu can be given by m1 into m2 upon m1 plus m2. Okay, that is a reduced mass. Okay, all these things we know. In this case, omega bar is equal to omega upon c is equal to 1 upon, therefore this term is also 2 pi c k upon mu. This frequency is in the form of the hertz or cycle per second, and this frequency in the form of centimeter, omega bar. Okay, therefore the spectra is expressed in the form of the centimeter inverse. Okay, like that, this formula is, remember this formula is, remember, we will write this formula in this side. Omega is equal to 1 upon 2 pi under root k upon mu, and omega bar is equal to mu omega upon c 1 upon 2 pi c under root k upon mu. This equation we have learned. All these terms we have learned. Now, according to the wave mechanics, quantum mechanics, the energy for this can be given as E for that mu is equal to 1. First level is equal to that V plus 1 half. V is the, that is level. V is equal to 0, V is equal to 1, that is the V is equal to that, not frequency. You remember, this is the quantum energy levels. V is equal to quantum energy level is equal to Hc into your omega bar. Okay, if you try to convert this equation in the form of only omega, then we know that omega bar is equal to, if you put that particular value, Hc omega bar. Okay, this omega upon c, omega bar is nothing but the omega. If c is cancelled, you have the equation V plus 1 half h mu. Okay, this equation, if you consider h mu, energy is equal to h mu, and if n, that n in this case, okay, n h mu for a frequency, if you consider, that is consider u n and h into v or h into omega. Okay, that's frequency. Omega is nothing but, and this quantity is n, is nothing but the energy given by the our Planck constant. Okay, but this energy is in the form of joule, and if you try to that energy is convert into, okay, that if you try to convert that energy, okay, the energy upon Hc, okay, therefore we have to also divide Hc. Then this will be energy you are in the form of mu bar. Okay, therefore is equal to V plus 1 half Hc upon Hc mu bar. Therefore your equation will be 1 half V plus 1 half omega bar. This is your equation you is obtained from your that particular equation. Okay. And this is all about we have seen. This will remove. Okay, therefore let's try the energy for each level by putting the value is equal to 0. Okay, energy of each level. Okay, this equation we will write to that side. E, okay, our useful equation V plus 1/2 omega bar. By using this equation, you can find out the energy of each level. Okay, first level. Okay, and when we studied the microwave spectroscopy, the energy of microwave spectroscopy in this level was 0. But this, let's try to find out what is the energy at that point by putting the value for energy is equal to V is equal to for 0. If you put V plus 1/2 omega bar, you put the 0, you will observe the energy is equal to 1/2 omega bar. Therefore, at a very low temperature or absolute zero temperature, your molecules is not in stationary, it's somehow there is a vibration is there, and some vibrational energy is associated with the molecule at a resting state. That energy omega 1/2 is we consider as the 0 point energy. Okay, molecule at 0 level, it should have some energy, and that is 1/2 omega bar. Okay, when you put the second energy is equal to 1, it puts the 1 plus 1/2, therefore 2 plus 1 upon 2, 3/2 omega bar. Then next level 5/2 omega bar. Okay, so on. Then next level 7/2 omega bar. Next level 9/2 omega bar. Okay, for this each level there is a energy you will observe. Okay, if you try to subtract energy, the difference between energy, then 3/1/2 by 1/2, okay, 3/1/2 minus 1/2 you consider, you will find 3 minus 2 upon 2 is equal to 1. Therefore difference is omega bar. Each term your difference is the omega bar. Okay, for this general equation, if your molecule is excited from energy level V to the energy level V plus 1, then we can find out this is if it's is it match, we can find out. Therefore we have the equation E is equal to your excitation is V plus 1. Okay, therefore first you have to put V plus 1. Okay, that instead of V, because it's excited, 1/2 omega bar plus V plus 1. Okay, sorry, in this case V plus 1/2 omega bar. Okay, therefore omega bar will consider is the same. We put this outside, therefore V plus 1. Okay, that is minus we should have, because difference is we are calculating the distance. V plus 1/2 plus 1/2 minus V minus 1/2. Okay, in this case you found that the V is the cancel, 1/2 is the cancel, only one term is which is having the no value, therefore omega bar. Okay, this is matched with the difference between two each energy level is omega bar, and you found that you found only one frequency in your IR spectra, that is omega bar. Okay, this is all about the IR spectroscopy. I hope you got this. Thank you very much.